Good morning, sir.
Good morning, sir.
Screen visible? The screen is visible?
Yes, sir.
Yeah. Okay, let us pass on to the next part of third module. Is ART network, or it is called as adaptive resonance theory neural network. ART network or adaptive resonance theory neural network. So ART network or ART was invented by Stephen Grasberg in the year 1976. So it is also a part of family of neural networks, and ART works on unsupervised learning model. The basic ART system works on unsupervised learning model. So the other things what we saw in the previous versions till module 2, so it was supervised learning model, but module 3 completely it is unsupervised learning model. It is similar to SOM, self-organizing maps. In the case of ART network, we need to know on two important terminologies. So one is considered as stability, next one is considered as plasticity. One is considered as stability and the next one is considered as plasticity. So these two terms we need to know. What is plasticity, what is stability? Because in the ART network, always we have a dilemma between these two terminologies. Stability plasticity dilemma or plasticity stability dilemma, whatever may be the case. So before entering into the plasticity or stability dilemma, so we need to know about one more terminology called resonance. The term resonance is nothing but it refers to the resonance state of the neural network. Resonance is nothing but it refers to the resonance state of a neural network. So resonance state is nothing but so whenever I supply any input vector, it tries to accept those input vector. The ART network tries to accept that input vector, current input vector, and it processes it and it tries to categorize that input vector into any one of the clusters, or any one of the groups. So that is considered as resonance state, or it is considered as resonance. So the term resonance is nothing but resonance state of a neural network. So whenever I supply an input vector, the input vector is accepted by the ART neural network and it tries to categorize that input vector into an existing clustering groups. So either it may be cluster 1 or it may be cluster 2 or it may be cluster 3. So it may be exact match or close match to the current input vector. So the ART, this type of matching procedures or this type of mapping procedures in the resonance state, this complete process, we call it as learning process. That is nothing but accepting the input, processing the input, and throwing the output. That is nothing but throwing the output as exact match in any one of the clusters, like cluster 1, cluster 2, or cluster n. And this complete process in the resonance state may be considered as learning, of an ART network. So, and this ART network only learns in the resonance state alone. Then the next one is nothing but the plasticity. What do you mean by plasticity? So plasticity is nothing but the world is full of information. So whenever you go to any place or whenever you go to any environment, okay, so you may learn new things. For example, you drive a motorcycle. Okay, today you drive a motorcycle means you had a different experience. But the same motorcycle, if you drive by tomorrow on the same road or on the same path, you may have a different experience. The third day, you may have a different experience. Fourth day, you may have a different experience. So that is nothing but these experiences are considered as learning. These different experiences day by day, you drive a motorcycle or you ride a motorcycle, that may be considered as a different type of learning experiences. So whenever the learning experiences are what you can call it as updating ourselves, learning experiences are updating ourselves, we try to what lose certain experiences which has been learned in the past, or we try to forget, either we try to lose or we try to forget certain experiences, okay, which we learned in the past. So if a network or if a neural architecture, if a network or neural architecture, okay, wants to maintain that plasticity. Plasticity is nothing but, so I have learned certain things in my 5 years of old, or I have learned certain things in my 10 years of old. I have learned certain things in my 15 years of old. So I should not forget that 5 years or 10 years. Okay. So I need to prevent those learning strategies, or I need to remember those learning strategies. So if I try to remember those learning strategies, in addition to the new learning concepts, like remembering the 5 years learning concept and 10 years learning concept, also remembering the 15 years learning without forgetting that. So that is considered as maintaining the plasticity. So the art neural network algorithm maintain the plasticity required to learn new patterns while preventing the modification of pattern that have been learned previously, while preventing the modification of pattern that have been learned previously. So I should not forget, or I should not change, or I should not mislead any information whenever new things come to my mind. So that state is considered as maintaining the plasticity state. So what is stability plasticity dilemma? That is the important terminology we need to know in terms of art neural network. So we say that the real world is faced a situation where data is continuously changing. Today something will be there. Tomorrow you go on that particular road or particular direction. There may be some update over there. Day after tomorrow, there may be some update. After a week, there may be some update. After a month, there may be some update. That's why they say that the real world is faced a situation where data is continuously changing. In this situation, every learning system faces a stability plasticity dilemma. So what is stability plasticity dilemma is nothing but, so system behavior does not change after irrelevant events. So whenever there is a continuous change day by day as the days progressing or as the days are moving, okay, so I should not change my behavior. I should not change my behavior. That is considered as stability. System behavior does not change after irrelevant events. For example, so you be called as a 9-pointer in the class. So you are the 9-pointer in the class. So as soon as you become a 9-pointer in the class, you should not change your qualities. You should not change your behaviors. Okay, I'm a 9-pointer. I will be like this. Okay, so you should not change your characteristics. Okay, so that is very, very important. Okay, next one is nothing but plasticity. Plasticity is nothing but adopts its behavior. The system or the network adopts its behavior according to significant changes. So whenever any new things are there, whenever any new things are observed, or whenever the data is continuously changing, I try to adopt that new behavior or adopt that behavior according to the changes, without forgetting the old information, Then what is the dilemma between these two parameters? One is stability and the next parameter is nothing but the plasticity. So how to achieve stability without rigidity and plasticity without chaos? So how to achieve stability without rigidity. Rigidity is nothing but, so I have certain constraints, I have certain defined conditions or defined boundaries. So within that, I need to achieve this stability. That will not happen. That may not happen. So I need to achieve the stability. That is nothing but behavior should not change. Behavior of the system should not change, even though there are certain irrelevant events, or even though the environment is continuously changing. So I need to be stable. I need to be stable in that particular situation. So how to achieve that without any rigidity, without any conditions, without any constraints, without any what do you call it as any type of other modifications or changes. And the next one is nothing but the plasticity. Plasticity means nothing but adapting to the current behavior. Adapting to the current behavior. So adapting to the current behavior is how it is important, how much it is important. In the same way, without any chaos, without any chaos. So it should not disturb the environment. It should not disturb the working culture, or it should not disturb the current scenario. So that is also very much important. So how to achieve stability without rigidity is important. The same way, the achieving the plasticity without any chaos is also very much important. Then the next one is nothing but, so how our learning capability is done. So the current learning capability, or it may be considered as ongoing learning capability. So how we learn, or how we observe, or how we experience the current environment or the given environment. Then the next one is nothing but the preservation of learned knowledge. So whether we are remembering, or whether we are able to recognize, or able to recollect the previous experiences or past experiences, so that that can be mapped to the current scenario, or to the current situation, where we can able to achieve this stability without any rigidity, or achieve this plasticity without any chaos, without any issues, or without any problem. Next one is, so how does the system know to switch between its plastic mode to the stable mode? So plastic mode is nothing but, so does not change after irrelevant changes, and stable mode. And plastic mode is nothing but adapting its behavior. Plastic mode is nothing but adapting its behavior. So how does the system know how it has to switch between its plastic mode to stable mode? So the ARP network tackles this kind of a situation. So ARP network tackles this kind of a situation. What kind of a situation? Switching over between the plastic mode and the stable mode, and trying to handle this dilemma without any rigidity, and without any chaos. Plasticity without any chaos, and stability without any rigidity. It is trying to tackle this ARP network. So ARP network and its algorithm maintain the plasticity required to learn new patterns, while preventing the modification of pattern that has been learned previously. So I had certain experiences in the past, or in the previous states. So I am not going to modify, or I am not going to do any modifications, but I try to learn certain new things, and I'm trying to store it in my memory, or store it as part of my process. So how it solves the stability plasticity dilemma is nothing but, it tries to form, the ARP network tries to form new memories. New memories in the sense is nothing but, either it may be considered as a short-term memory, part of a short-term memory, or part of a long-term memory. It tries to form certain new memories, or incorporates new information based on the predefined vigilance parameter. Predefined vigilance parameter is nothing but whether this information is needed or not, whether this particular data is needed or not, whether this particular parameter value is needed or not, whether this particular what you can call it as steps or procedures are needed or not. So that is nothing but it tries to form these new memories, or tries to incorporate the new information based on certain predefined vigilance parameters. So based on certain conditions, based on certain constraints, so whatever is relevant to that it will group, and it will form a new memory, and it will try to solve that particular issue called stability plasticity dilemma. So the key innovation in the art architecture. So what is the key innovation? The key innovation of art architecture is the use of expectations. So use of expectations. The expectations here is nothing but, so whenever I present an input to the network, art network, whenever I try to present an input to the art network, it is compared with the prototype vector that is mostly matches to the input vector, then that is considered as expectation. So whenever I supply any input, I have already predefined categories, or I have already predefined clusters, or I have already predefined groups. So this particular input, okay, whichever has been presented to the network has to, okay, match any one of this following categories. So that may be considered as a expectation of the user or expectation of the operator. So if the match between the prototype and the input vector is not adequate, then a new prototype is selected. If it is not matching in any of these clusters or any of these groups or any of this, what you can call it as any of this particular modules, so it may try to create a new prototype, or a new prototype is created. A new prototype will be created. In this way, previous learned memories are not eroded by new learning. So already existing is available. For example, there may be 3 clusters or 3 groups may be available, but it is not matching. It is not adequate. My match between the prototype and the input vector is not adequate. In such a cases, a new prototype will be selected. So my past learning will not be also eroded, will not be also deleted, or will not also be corrupted, but also I try to preserve the new prototypes into my art memory. So art network consists of only 2 layers. One is considered as input layer and other is considered as output layer. And also it uses, since it has 2 layers, it is similar to a BAM network, bidirectional. So it uses both types of weights. One, it consists of bottom-up weights, and other it is nothing but the top-down weights. Art network uses 2 types of weights. One is bottom-up weights, which is used to determine output layer candidates that may best match the current input. Art uses the bottom-up weights are used to determine the output layer candidates that may best match the current input. So whenever I try to supply an input vector or input into the input layer, so it tries to find out a match, exact match with the prototype of that input, and it tries to group them in any one of these clusters or any one of this divisions. So in such cases, if there exists a best match, means then the bottom-up weights will be used from input to the output layer. Top-down weights are nothing but used to represent a prototype for the cluster defined by each output neuron. Top-down weights is nothing but from the output layer to the input layer. So it is trying to represent a prototype. So either it may be in the predefined clusters, or it may form a new prototype and a new cluster may be formed. A close match between the input and prototype is necessary for categorizing the input. That is nothing but which category it belongs to, either category 1, category 2, or category N, of like that, which category it belongs to. So finding this match can require multiple signal exchanges. So for finding this match, it requires multiple signal exchanges between this input layer and the output layer in both the directions until resonance is established or new neuron is added. Resonance is established is nothing but either a match has to be obtained or a new prototype has to be added. A match has to be obtained or a new prototype has to be added over here. So this is the basic art network architecture. So it consists of 2 layers. First layer is considered as the input layer, which is considered as F1 layer, and the second layer is considered as F2 layer, which is considered as output layer. So the input layer is considered as comparison field. Input layer is considered as comparison field, and the output layer is considered as an recognition field composed of neurons. And we have one more thing called vigilance parameter. So rho. So based on the vigilance parameter only, so I try to obtain this plasticity as well as stability dilemma, or I try to tackle this stability and plasticity dilemma with the help of this vigilance parameter called rho, which is available in the reset module, So this F1 is nothing but comparison field, F2 is nothing but the output layer, and this vigilance parameter is rho, and it is nothing but the reset module. So there are two layers of neurons and reset mechanisms. So one is considered as the F1 layer, an input processing field called the comparison layer, and F2 layer considered as the cluster units, where I am trying to group either group 1 or group 2 or group 3 or group 4 or group n. So that is nothing but cluster units is also called as competitive layer or recognition field. Then the reset mechanism, that is nothing but your reset module. It is used to control the degree of similarity of the patterns placed on the same cluster. So how close this particular input pattern can be mapped to this particular cluster, how close it can be mapped to this particular cluster. That is nothing but degree of similarity of the patterns placed on the same cluster takes decision whether or not to allow the cluster unit to learn. Then there are two sets of connections over here. So one is nothing but the bottom up weights. This is this arrow, and next one is nothing but top down weights. This is nothing but this arrow. So the bottom up weights is nothing but from each unit of the layer F1. This is one unit, unit 1, unit 2, unit 3, each unit of layer F1 to all units of layer F2. All units of layer F2 it may be going. Then the top down weights each unit of layer to all units of layer F1. F2 to F1 is nothing but top down weights, and F1 to F2 is nothing but bottom up weights. Okay, so from bottom up means it may be represented as W, from top down means it is represented as Z value. So this is the basic architecture. You have two layers. One is input and other one is the output layer. That is nothing but your cluster or competitive layer. So this layer 1, that is nothing but our input layer is divided into two divisions, which is called as first division is considered as layer input portion, where I try to supply the input patterns over here. S1, S2, S3 up to Sn. And second portion is nothing but interface portion, which is acting as an intermediate between this layer input portion and the layer output portion is nothing but cluster units. So this bottom up weights is represented by Tij. Bottom up weights is nothing but from Tij, and top down weights is nothing but Bij. See here, Tij is bottom up and top down is nothing but Bij. So art subsystems. So what is available here? So it consists of layer 1, which is considered as L1. That is nothing but the comparison of input pattern and the expectations. Expectations is whether match is available or not. Then it is having connections between L1 and L2, layer 1 and layer 2. And each row of weight is a prototype pattern. This one, each row of weight is nothing but a prototype pattern. Then layer 2, it is a competitive layer. This green color is nothing but a competitive layer where winner take all learning strategies. And here also you have weight connections from L2 to L1. Weight connections are there. It performs a pattern recall, that is nothing but the expectations. Then again we have a orientation subsystems, that is nothing but your reset module, which causes expectation does not match the input module means then I need to use this orientation subsystem. So where the reset module can be working in this orientation subsystem. Then the next one is nothing but the vigilance parameter. So that is nothing but it is used to find out whether any new pattern is going to be added or there is an exact match between the input pattern and the prototype vector. So this vigilance parameter is controlled by a user defined gain control factor, that is considered as rho. So art algorithm. So you have new pattern whenever I try to introduce a new pattern. That is nothing but the new input. So it is trying to categorize that new pattern. So whether it is known pattern or unknown pattern, it is trying to categorize whether it is known pattern or unknown pattern. If it is known pattern, adapting to the winner node, that is, it may be forwarding it to or mapping it to the exact cluster. If it is an unknown pattern means, so it is trying to initialize uncommitted node and then it tries to recognize those things and then it tries to compare it. Then if exact match is there, it will form a new cluster, or it may map it to the existing cluster or the corresponding cluster. So the incoming pattern is matched with the stored cluster patterns. If the incoming pattern close enough to the stored pattern, it joins the best matching cluster, weights are updated. If not, a new cluster will be initialized with the pattern as a template. What are all the various types of ART networks? All the various types of ART networks. There are two types of ART networks are there. One is considered as unsupervised ART and the next one is considered as supervised ART network. So in the case of unsupervised ART, we have various types. One, it is called as ART1, ART2, ART3 and fuzzy ART map. Next one is nothing but fuzzy ART. Next one is in the case of supervised. So it is having two types. One is considered as ART map and next one is considered as fuzzy ART map. So what is ART1? ART1 is nothing but the simplest version of ART network or the simplest form of ART network which accepts only binary inputs. ART1 is which is the simplest form or simplest version of ART network which tries to accept only the binary inputs. And ART2, it supports continuous inputs. Continuous inputs is nothing but, so we say that the world is full of information, that the data keeps on continuously changing. So ART networks tries to support only the continuous inputs, and ART1, it tries to support only binary inputs. Then the next one is ART3, which is nothing but a refinement of both the models, ART1 and ART2. It is nothing but the combination of ART1 and ART2. There's nothing but refinement of both ART1 and ART2. Then the next one, fuzzy ART. Fuzzy ART is nothing but it implements a fuzzy logic into ART's pattern recognition. So what is the ultimate objective of this ART architecture? It is nothing but it is trying to recognize a pattern and it is trying to push that pattern to the specified cluster or to the corresponding cluster. So either cluster 1, cluster 2 or cluster 3 or group 1, group 2 or group 3. So that is nothing but the fuzzy ART network. So in addition to the ART network, it uses the fuzzy logic rule base or fuzzy logics, what you can call it as inference engine, so that the ART can able to recognize the pattern in an effective and efficient way, and it can push it to the corresponding cluster or map it to the corresponding cluster, or you can try to identify a new cluster also. Next one is nothing but the first four what we saw, ART1, ART2, ART3 and fuzzy ART are considered as unsupervised ARTs, Now the ART map and fuzzy ART map are considered as supervised learning structure. So ART map also known as predictive ART. ART map also known as predictive ART, which combines two slightly modified ART1 and ART2 units into a supervised learning structure. It is considered as predictive ART. It slightly modifies ART1 and slightly modifies ART2, and then it is considered as a predictive ART or ART map, and it uses a supervised learning structure instead of an unsupervised learning structure. Next one is nothing but fuzzy ART map. Similarly, we are trying to merely ART map using a fuzzy ART units, like how fuzzy ART we are using, like that ART map we are using a fuzzy ART units, resulting in the corresponding increase in the efficiency of the things. So what are all the applications of ART? What are all the applications? So it may be used in the mobile robot control, then it may be used in the facial recognition and target recognition and pattern recognition problems. Then it may be used for land cover classification in the geo-specific or geo-information systems. Then it may be used in the medical field like medical diagnosis and signature verification things. Then how the art algorithm works. The description of the algorithm. So ART1, it accepts the binary input. So binary input vector is applied to F1A. F1A is nothing but the layer, input portion layer, which accepts the input. F1A is nothing but F1 is considered as input. So the input is segregated into two layers. One is considered as layer A, which accepts the input, and layer B is nothing but which transforms that input to the what you can call it as the output layer called F2, which is nothing but the cluster layer, or which is nothing but the competitive layer. So the binary input is supplied, that is it is supplied to F1A layer and it is forwarded to the and then it will be forwarding it to the F2 layer over weighted interconnections. F1A to F1B and F1B to F2 over weighted interconnections. Next one is nothing but next part. So each neuron at F2 is nothing but cluster units only. Each neuron at F2 will calculate the net input. So how it will calculate the net input? Via dot product of input vector and its associated weight values. Via dot product of input vector and its associated weight values. So the it calculate the net input over here via dot product of the input vector is nothing but this into weight values. Then the neuron with the highest net input. So you may have multiple neurons will be there. Neurons with highest net input will win and learn new pattern, and the activation for that neuron will take place. Activation for that neuron will take place. This is the basic ART algorithm working principle. So what are all the parameters used in the ART algorithm? So n is nothing but number of component in input vector, and m is nothing but maximum number of clusters that can be formed. And Bij is nothing but bottom up weight. Bij is nothing but bottom up. Is set by the user tester for testing the acceptance level for the cluster. Then the next one is nothing but S is considered as binary input vector, which is supplied to F1A, F1 layer of A portion. Then X is nothing but the activation vector for F1B. Then modulus of X is nothing but the norm of vector X, which is nothing but sum of all Xi. These are all the parameters we used in the algorithms. Next one. So what are all the initial parameters used in the algorithms? So initial parameters used in the algorithm is nothing but parameter L. So its permissible range is greater than 1. So parameter L, its permissible range is greater than 1. Next parameter is nothing but rho, which is considered as vigilance parameter. It takes the value between 0 to 1. So it takes the value between 0 to 1. And this, what is this L is nothing but the bottom up weight should be smaller than or equal to 1. So it should be smaller than or equal to 1. So Bij, okay, Bij should be lies between 0 to L divided by L minus 1 plus N, bottom up weights. Next one is nothing but top down weights, which is nothing but Tji. Top down weights is nothing but Tji, always it is initialized to 1. Top down from here to here, T21, T22, T23, T2N. So this may be considered as top down weights. Always it is initialized to 1. So steps to perform the ART algorithm. So updates for both bottom up and top down weights are controlled by the differential equations. Updates Okay, then step number 1, I need to initialize the parameter L greater than 1. And rho is nothing but the vigilance parameter between 0 to 1, and I try to initialize the weights. So bottom up weight should be smaller than or equal to 1, and top down weights always initialized to 0. So Bij equal to Lxi divided by L minus 1 plus modulus of x. And step number 2, while stopping condition is false, I need to repeat the steps 3 to 14. And what is step number 3? For each testing input, I need to repeat the steps 3 to 13. So what is step number 4? I need to set the activation for all F2 units to 0, activation to 0, and set F1 of A activation, set F1 of A, that is nothing but the input layer activation to input vector yes. Why? Because so F1A is nothing but yes, as shown in the diagram. This is set to yes, the inputs. Then the next one is step number 5. I need to compute the norm of S. This is nothing but modulus of S equal to summation of S of I. Then step number 6, I need to set the input signal from F1A to F1B. So this one. So Si to Xi, F1A to F1B. So Xi equal to Si. Then step number 7, for each node of F2 that is not inhibited, if Yj not equal to -1 and Yj equal to summation of Bij Xi. So that I need to do in step number 7 for each node in F2. For each node in F2, I need to do that. And step number 8, while reset is true, I try to do the steps 9 to 12. So find j such that Yj greater than Y of j for all j. If Yj is equal to -1, then all nodes are inhibited and selected cluster cannot be trained. Then step number 10 is nothing but I need to recompute activation of x. That is nothing but F1B. So Xe of I equal to S of I into Tj of I. So this is nothing but the weights and this is nothing but the inputs. So I need to compute the norm of x, modulus of x equal to summation of xi as previously. Then step number 12, I need to test for reset. Modulus of x divided by modulus of s less than rho is nothing but the vigilance parameter. If it is Yj equal to -1, the cluster cannot be trained. So I need to do the step 8 again. And then I 8 to this one, 8, 9, 10, 11, 12 I need to do. So then step number 13 is nothing but I need to update the weights of the node j. So Bij new equal to x. L into xi divided by L minus 1 plus modulus of x. And Tj is nothing, this is bottom up and this is top down. Nu equal to x of I. Then I'm trying to test for the stopping condition. If it is satisfied, then I'm going to stop my iteration. If it is not satisfied, I'm going to continue this process. So in simple, only these 4 steps I need to follow ABC. So first initialize the top down values T of Ij equal to 1. Bottom up weights equal to 1 divided by 1 plus 1 divided by n plus 1. While the network has not stabilized, I need to present a randomly chosen pattern X for learning. Let's set the let the active set A contain all the nodes. Calculate Yj equal to Bj, comma 1 plus into x1 plus Bj, comma 2 into x2, like that it goes on. Then I need to repeat this process. Let J star be the node of A with the largest Yj. Then with the ties being broken arbitrarily, then I need to compute the S star. And then I need to compare the similarity between S star and X with the vigilance parameter using this formula. Else, I need to associate, that is nothing but associate X with the new node J, and I need to update my weight values, same formula with respect to previous one. And until A is empty or X has been associated with some node J in the cluster units. If A is empty, then create a new node whose weight vector coincides with the current input pattern, and I'm trying to end my things. So the example we will see tomorrow. So I'm winding up today. Shall we wind up?
Thank you, sir.
Okay.
Yes.